Okay, so in this video, we're going to be talking about the difference quotient and how to find the difference quotient and what the difference quotient is. So why don't we start with what is the difference quotient? And it's pretty straightforward. The difference quotient is how you can find the derivative of a function. So what is a derivative? Well, a derivative is the instantaneous rate of change at any point on a function. Okay, so for example, you can see I have my function here, f of x, being graphed on my coordinate grid here. And again, we're in the first quadrant here. So what we want to look at is how do we find the difference quotient? Because once we find that, then we're going to be able to find the derivative of various functions. So again, once we derive the difference quotient, I'm going to have examples at the end of this video on how we can actually use it to find the derivative of two different functions. Okay, so make sure you stick around for the end. And with that being said, let's go ahead and find the difference quotient, and then we'll talk about how we're going to use it. So again, we have my function here, f of x, and you can see the curve of it, right? And so what you want to do first is put a point on that curve. So I'm going to go ahead and put a point anywhere on this curve. I'll go ahead and put it right here. And we want to go ahead and label that point. Now, we're given no information about this function f of x. So based on just the fact that I know that this function is f of x, I'm going to call this point x, comma, f of x. Okay? And again, we know that f of x is our y value. Okay? And then I'm going to go ahead and put another point on. So I'm going to go ahead and put another point on. I'll put it over here. And again, it could be anywhere. And how do I describe that point? Well, what we're going to have to do here is we're going to have to go ahead and put on a distance going from this point to this new point that I just put on. So I'm going to go ahead and draw a vertical line coming down here. And I'm also going to draw a vertical line coming down here. That way we can describe that distance as h. So we're going to describe this horizontal distance going from my first point to my second point as h. So I'm going to go ahead and put h here. And now that I have that distance defined as h, I can go ahead and put on my new point. It's going to be x plus h. That will be my x value, right? Comma f of x plus h. Okay? So again, I know that going from here to here, that's going to be a distance of h. So if I just add x to that, that gives me the x value of this point. And then this y value, f of x plus h, that's essentially me taking this x value right here, whatever it may be, and plugging it into the function that will return the y value, okay? So I essentially have 2 points here on this curve. And again, all I know about this function right now is that it's f of x. But I don't really care what it is because we're going to derive the difference quotient that, again, will give us the ability to take the derivative of a function. So we talked about how the derivative is essentially the instantaneous rate of change, okay? And so when you think of rate of change, you need to be thinking slope, right? So I'm talking about a slope here. So what I'm going to go ahead and do is label these points like you normally would when you're finding the slope between 2 points. So I'm going to go ahead and say here, this is x1, y1, and this is going to be x2, y2. And again, we know that the slope between 2 points is going to be y2 minus y1 all over x2 minus x1. Okay, so we're going to use that to our advantage here. So why don't we go ahead and do that? So I'm going to go ahead and scroll down. That way I have room to do what I need to do. And I'm going to go ahead and start plugging this stuff in. So I'm going to do y2 minus y1. That gives me f of x plus h, okay, minus y1, that's going to be f of x. Okay, all over. And we're going to say here x2, that's x plus h. So x plus h minus x1, that's going to be x minus x. So you can see here that the x's will cancel. Okay, these cancel. And I'm left with f of x plus h minus f of x all over h. Okay? So what you just found was the slope between these 2 points here. So this point here and this point here. But again, remember the definition of a derivative. A derivative is the instantaneous rate of change, okay? So right now we have our difference quotient right here, okay? But again, I want to be able to use it so that I can find the derivative. So what I need to do is the following. I have to put a limit on h. In other words, I have to say a limit on h as it approaches 0. So if we do that, think about what happens here. This slope that you have between these 2 points, if you put a limit on h as it approaches 0, you're essentially shrinking this horizontal distance to eventually you get to this instantaneous rate of change on this point right here, okay? And when you do that, the line always ends up being tangent to the curve, okay? And it could be at any x value on this curve, okay? And so if I put a limit on h and I say as h approaches 0, you no longer have a slope between these 2 points, but what's happening, this is shrinking and it's going in this direction here until eventually you have this instantaneous rate of change that ends up being tangent to this curve like this here. Okay, so you end up having this instantaneous rate of change. And again, that is going to be your slope. And again, this slope will end up being tangent to this function f of x. Okay, and it can essentially occur anywhere on this curve depending on what you plug into the x value once you take the derivative. Okay. But the takeaway here is the derivative is the instantaneous rate of change, and that always ends up being tangent to the curve. So what we can say here, I'm going to go ahead and scroll down, we can put it all together. I can now say that f prime, and f prime means the derivative of f of x. So f prime of x is equal to f of x plus h, okay, minus f of x all over h. And again, we do want to put a limit on this. We want to put a limit on h. So we're going to say here limit as h approaches 0. There we go. Okay. So we can now use this to find the derivative of various functions. Okay. So that is the difference quotient. Now let's go ahead and talk about how we can apply it to functions again to find the derivative. So here we have a function f of x, and its f of x is equal to x squared. Now I want to make it very clear here. This is very simple to get the derivative, okay? Once you understand calculus, it's very simple to get the derivative of this function. But again, using the difference quotient is the most foundational way to get the derivative, and it gives you a deeper understanding of where this is coming from. And it gives you an understanding that, hey, the derivative is actually the instantaneous rate of change, okay? So just keep that in mind. You could get the derivative of this function in less than 5 seconds, but we're going to use the difference quotient to go ahead and illustrate how we can use that to get the derivative of a function, all right? So I'm going to go ahead and write the difference quotient right now. It's going to be f prime of x. And again, we have that limit on h as it approaches 0. And we're going to set this equal to, again, f of x plus h, then minus f of x all over h. And so now you can see in action how it's going to work. Okay, so again, here it is. And so let's go ahead and use it now to find the derivative of f of x. So what this is telling me to do, wherever I see an x, the first part I have to plug in is x plus h. Okay, so here's my x right here. I have to plug in x plus h and then square it. So I'm going to go ahead and do that. I'm going to have x plus h and then square it. And then what comes next? So I did this part right here. Now I have to move on to this part right here. I have to minus f of x. Well, what is f of x? It's going to be x squared, right? So I'm going to go ahead and put minus x squared here, okay, all over h. So from here, you have to expand it out. You have to do FOIL here, right? First, outside, inside, last. That's a binomial being squared. When you do that, you should get x squared plus 2xh and then plus h squared and then minus x squared. And again, this is all over h. From here, we want to clean it up, okay? So I can see that I have x squared here and negative x squared here. That cancels out, okay? Then, is there anything that you can factor? So look at your numerator. You can go ahead and pull out an h. If you pull out an h, what happens? So pulling out a greatest common factor there, again, pulling out that h, you get h times 2x and then plus h. And again, this will all be over h. And so now the h's cancel. And remember, we're putting a limit on h as h approaches 0. So there's nothing else I can do in this problem, but remember this h here, I have to put a limit on it as it approaches 0. So this h is essentially gone now as I put a limit on it, right? As it approaches 0, it becomes 0. And I'm left with 2x, and that is your derivative. So you're going to say here f prime of x is equal to 2x. Okay, and that's it. And so this right here is our final answer, right? So again, we just used the difference quotient to find the derivative of this function. And again, just keep in mind, this represents the instantaneous rate of change. Notice how you have an x value here. I can plug any x value that occurs on that curve of that function, and that gives me the instantaneous rate of change at that particular point on that function, okay? But again, this is essentially the derivative of the function. All right, let's go ahead and try another example. So here's our next example. This one's going to be a little more challenging. I'll go ahead and write out the difference quotient again. That way we have it. So it's f of x plus h minus f of x all over h. And again, we do know that we have a limit on this as h approaches 0. I'll go ahead and write that right here in case we forgot. But we do have a limit, right? So how do we do it? So the first thing we have to plug in is x plus h wherever we see an x. So this one's going to be a bit longer. You're going to have 2 and then times x plus h and then square it, okay? Then plus 5 times x plus h and then minus 2, okay? So I'm done with that part. Now I can move on to this part here. I essentially have to subtract the function f of x. So I'm going to say here minus, and then in parentheses, I'm going to put 2x squared plus 5x minus 2. Close it. All over h. So this whole thing is over h. Okay, so now comes the fun part. We get to expand it out. So going left to right, I have x plus h squared. I can use FOIL to expand that out. When I do that, I get the following. I get 2 times x squared plus 2xh plus h squared, and then we close it. Okay? Then I can take this 5, I can distribute inside. I get plus 5x plus 5h, okay? Then minus 2. And then again, this negative here is going to change the signs of all of my terms inside parentheses here. So I'm going to go ahead and put negative 2x squared minus 5x and then plus 2. And again, this whole thing is going to be over h, okay? So what can we do from here? Well, first I'm going to go ahead and scroll down. That way I have room. And we're going to go ahead and keep cleaning it up. So now I can take this 2 and I can distribute inside. That's going to give me 2x squared plus 4xh and then plus 2h squared. And then I have plus 5x plus 5h minus 2 and then minus 2x squared minus 5x plus 2, and again, all over h. Okay, can I clean up my numerator? And yes, I can, right? There's going to be some terms that will cancel out here. So I have a 2x squared and a negative 2x squared. Those cancel. What else can I do here? Well, I have a positive 5x and a negative 5x. That cancels. I have a negative 2 and a positive 2. That cancels. And from here, there's nothing else I can really do, but I'm going to go ahead and rearrange the order here. So I'm going to go ahead and scroll down a little bit further. And rearranging it, I'm going to say 2h squared plus 4xh and then plus 5h all over h, right? And so from here, what can we do? Well, I can factor out an h on my numerator, right? I can pull out a greatest common factor. So when I do that, I can pull out an h and I'm left with 2h and then plus 4x and then plus 5. Okay? All over h. So the h's will now cancel. This cancels, this cancels. And remember, we have a limit on this as h approaches 0. So wherever you see an h, you are essentially making it 0. So I do have an h right here. I'm going to put that limit on it. And again, that's as it approaches 0. So this whole part right here is essentially gone. I'm left with 4x plus 5. So that is going to be the derivative of this function. I'm going to say here f prime of x is going to be equal to 4x plus 5. Okay, and that's done. So let's go ahead and box it in. And that is the derivative of the function f of x. Again, the instantaneous rate of change. So that is the difference quotient. That is how you use it to find the derivative of various functions. Again, I just want to make it abundantly clear here. There are easier ways in which you can get the derivative, but this is the most foundational way in which you can do so, and it gives you a deeper understanding as to how the derivative actually works and where it comes from. Again, the key takeaway here is that the derivative is the instantaneous rate of change, okay? And so that is it. I hope that you found the video helpful. I hope that you gained something from it. If the video did in fact help you, if you could just go ahead and give it a thumbs up, that would be greatly appreciated. Also, make sure you subscribe. That way you get more math videos in the future, and I'll see you in the next one.